start. So, good morning, everybody. I'm Aghiles Ait Messaoud, research software engineer at iExec. Today, we are going to tell you about how we are working at iExec on rethinking TEE Trust Models by securely scaling TEE-based services with hybrid remote attestations. So, the main problem we're addressing here is how to securely and efficiently deploy a cluster of TEE services, specifically SGX services. And when we speak about deploying such trusted services, we refer to the use of remote attestation in order to prove their trustworthiness. However, specifically when we are speaking about deploying a cluster of SGX services, we need to attest each node of these clusters individually, which brings its own of unique challenges that we are going to present a bit later. But before going further, let's recall some concepts of SGX remote attestation. When we are doing a remote attestation using SGX, there is 4 major actors. The first one is the SGX service itself, that we also call the attester. It is basically the SGX service that needs to be attested and that delivers the intended service to the client. Then we have the verifier who attests this SGX service cryptographically by leveraging the Intel PCS, that stands for Provisioning Certification Service. That is an Intel service that caches the Intel certificates needed to verify the attester or the SGX service. And finally, we have the client that verifies the attester and consumes its service. Here we need to stress about the difference between the verifier and the client. The verifier cryptographically verifies the attester by using some cryptographic primitives and the SGX SDK, for example, while the client only consumes the service and verifies it, or it just checks the result of verification performed by the verifier. Now, after presenting the most important concepts of remote attestation, we can present what are the limitations of the previous scheme by describing 2 different processes. The first one is a process of certifying or verifying an SGX service by the verifier. Then we have the process of the client-side verification. Let's start with the first process of certification of SGX service. In order to certify a new spawned SGX service that builds our cluster, the attester or the SGX service needs to generate a set of private key, public key inside its enclave. Then the attester embeds the public key part inside the code, which is a cryptographic summary of the enclave. Then it sends it to the verifier. Once they receive, the verifier checks the code using some libraries. And when we are speaking about checking the code, we means that it checks the hardware genuineness of the hardware that delivers the code, and also checking the application identity. Specifically the MR enclave or MR signer, etc. We can have different policies. Then after this, if everything is okay, the verifier delivers a verifier signed certificate to the attester. Now, the second step is the client-side verification of the SGX service, and in this step, the client gets the certificate that have been delivered by the verifier from the attester of the SGX service. Then the client gets the verification public key of the attester certificate in order to validate this certificate and check its genuineness. Then the client, at the third step, sends a challenge to the attester. The attester signs this challenge using its own private key that have been securely generated inside its enclave before responding to the client. Then the client verifies the signature with the public key that have been previously embedded in the certificate. If everything is okay, it means that the client can securely, let's say, interact with the SGX service. However, the main drawback of this scheme is centered around the verifier. Indeed, the verifier actually is the root of verification, and it is anchored let's say, on a non-attested entity, which means that the client blindly trusts the verifier about the decision it takes with regard to the SGX service. We also have the fact that the verifier is actually a centralized entity, which means that if it crashes, then there is no mean to attest new SGX services, and also we have a limited scalability for certifying decentralized services because we are relying on a single entity or a fixed number of verifiers. Now, what we are proposing to circumvent these problems is a solution built around 3 key principles. The first one is anchoring the root of verification on-chain, which means that the verifier is not anymore a single verifier, but indeed it is the blockchain, which is a set of decentralized, mutually entrusted nodes. Then our second key principle is delegated off-chain attestation, which means that after the blockchain having attested some set of nodes, then these nodes inherit the property or the legitimacy to attest new nodes by themselves. And finally, we have a protocol that easily allows a client to interact with a node through attest once and verify afterwards. Let's start with our first protocol, which is anchoring root of verification on chain. So you remember this scheme where we have a single verifier that the client blindly trusts because it delivers a certificate to the attester? What if we replace this verifier by the blockchain, which is technically a set of decentralized nodes, and that should be an EVM-based blockchain? And now we have a set of decentralized nodes that could execute the code in a secure manner using the consensus mechanism built by design inside the blockchain. But now we need a set of smart contracts that allows us to attest the code that is delivered by the SGX service. That's where our partners Automata delivers a set of smart contracts that allows us to perform on-chain code verification and also collaborative certificate asserting, because anyone can collaborate with Intel certificates through the blockchain. So we also have an Intel PCS on-chain. However, the smart contract delivered by Automata are not enough because they are only performing the verification of the hardware genuineness of the SGX service. So we have extended at iExec this smart contract in order to allow the application level verification of the code, which means that we attest that the code is genuine, it has been delivered by a real SGX enclave, and we also attest that the application is really what the application it claims to be. So we have an application level whitelisting where we whitelist the tolerated MR enclaves that could be executed in our cluster. We also have an application level verification of the code and also public key registry where we register the machines that have been tolerated by our protocols to be executed inside our cluster. And also we have a mapping between the IP address of each tolerated machine and its public key. And now, the main advantage of this approach of relying on blockchain-based attestation extended by our smart contracts is that the root of verification is not anymore tied to a single verifier, but on the blockchain that is a more legitimate verifier. Then we have a strong availability of verification because we cannot basically shut down the blockchain. However, the main drawback of this method is that we we have a limited scalability for attesting highly decentralized services because blockchain is known for its poor throughput in its base form. As an example, in order to perform a non-chain attestation, we need 6 million of gas, which constitutes a high fees and which gives us a limited throughput because we can only perform 5 on-chain attestation per block if we are referring to Ethereum blockchain. This is where we introduce our second contribution, which is delegated off-chain attestation, where basically we delegate to some nodes that have previously been attested by the blockchain the role to attest themselves new nodes of our clusters in order to have a bigger throughput. So let's assume that we have an SGX service that have already been attested on-chain, and conceptually an SGX service have 2 sub-services. We have an attestation service that gathers attestation requests and sends them, and in order to make the attestation and send the result to the blockchain. Then we have the business service that offers the intended business to the client. Now, let's assume that we have a new SGX service in our cluster, namely SGX service 2, that needs to be attested. Instead of directly attesting on-chain, the SGX service 1 can attest this new spawned SGX service. So literally, it will generate its own set of private key, public key pair inside its enclave and send its attestation data not to the blockchain, but to the already attested SGX service 1. Then this service will execute a set of verification, just like what we did on-chain, which means that we are going to verify the signature using the public key embedded inside the payload. We are going to check the hash of the code, check the code against Intel certificates using the official DCAP SGX SDK, and we are going to extract the MR enclave that distinguishes our application from the code. Then we are going to get from the blockchain the reference MR enclave or the ground truth MR enclave relative to the expected application, our application ID. Then we are going to compare this ground truth MR enclave with the MR enclave embedded inside our code. If everything is okay, it means that the attestation goes right, and we can now send the direct service registration request to the blockchain on behalf of the SGX service 2, which means that SGX service 1 will send a payload constituted by some data such as the IP address of the newly attested node, the IP address of the verifier that performs the attestation on behalf of the blockchain, and also the public key that have been generated on the newly spawned node. And everything, of course, should be signed with the private key of the already attested service, namely the SGX service 1. Once on the blockchain, it will just check the signature using the public key of SGX service 1, and we will register this service if everything is okay. At this step, we have registered SGX service 2 using our delegated off-chain attestation. Now let's move on in our last contribution, which is basically how the client interacts with any node of our cluster. And here, let's suppose that the client wants to interact with a service named SGX service, and to do so, it will send the application identifier to the blockchain in order to gather some important information, such as the IP address where this application is deployed and the public key related to this service. And then the client will perform what we call an authenticated Diffie-Hellman protocol. In cryptography, this is a protocol that allows us to create, let's say, a shared secret between two entities, here the enclave and the SGX service. And at the end of this known protocol Diffie-Hellman, we are going to have a secret key K that will allow us to establish a direct secure connection between the client and the SGX service. It is similar to how TLS is working by establishing a symmetric key between the client and the server. Now, let's show you some preliminary results that we have obtained using this protocol. The first result is directly tied to the design of our protocol. Indeed, we have an improved security because we don't need anymore to have trust assumptions since the root of trust is tied to the blockchain, but we just have security delegation. The root of trust is the blockchain, then the blockchain attests the first SGX service, the first SGX service attests other SGX services, and so on. So we don't need to blindly trust any verifier that is not binded to the blockchain. Our second result regards, let's say, the quantity of gas used during the attestation. If we have a full on-chain attestation, if you remember well, we have a cost of 6 million of gas. However, with our delegated off-chain attestation, we have 20 less gas and just around 15,000 of gas consumed, which means that we need way less fees in order to execute this attestation. Our last results regards the scalability of this approach. And here, what you are observing in the x-axis is the size of the cluster we are deploying. We have different sizes going from a cluster of 2 nodes until a cluster of 16 nodes. And here the machines of the clusters are simulated using processes. And on the y-axis, what you are observing is the time to deploy all the nodes of these clusters. If we use and here why we have many curves, it's just because we have simulated these tests using different configuration of machines with regard to the number of the CPUs of these machines. For example, if we have the main takeaway of this result is that the full on-chain attestation is as costly as if we have an off-chain verifier that have only 2 threads, which means that if you have a machine that have more than 2 virtual CPUs, it is more, let's say, more lightweight to perform the delegated off-chain attestation because you are going to have better performance. And finally, just to recap, these results have been obtained using a blockchain that have been simulated using the Anvil tool that is provided by the Forge team. And we have configured the block time of 5 seconds and the gas limit of 15 million gas per block. And thank you for your attention. If you have any question, you can ask it now or send it via Telegram.
Any questions? Raise your hand. All right. Round of applause again. Thank you.
Thank you.